Greetings everyone, this is Mr. Mull. I'm really excited today to help you out with determining an atom's electron configuration. The electron configuration of an atom is really the address that describes the location of each electron within an atom. I sometimes like to think of an atom as this hotel, okay, as a hotel. So the bottom of that hotel is my nucleus. And my electrons are obviously outside the nucleus, but they're not just in these perfect circles like Bohr predicted. They're in these weird things called orbitals, these high probability regions where the electron could be. So because they can be in these different regions, you know, my electron could be here, it could be here, it could be here, it could be there, it could be there, it could be there. What we can do is we can determine the location of, find out, okay, where is this electron to the best of our knowledge. We can't find it perfectly. Heisenberg said there's no way we can know the exact location or speed of that electron, but we can know the region it's in. An electron address is kind of like saying, okay, this is the room in my hotel that these electrons live. So there's different levels of the hotel, and the different floors of the hotel correspond to the energy levels. So as I go up in energy level, I get farther from the nucleus. As we get energy levels, so there's our first floor, second, third, fourth floor. So as I move up in energy level, I move farther away from the nucleus. And also, the radius is bigger. So these kind of orbitals and these areas of the floor actually keep getting bigger. So my hotel is kind of lopsided. It kind of, gets bigger as you go up, okay, from my little hotel. And in each floor of the hotel, there's some different levels of the hotel or wings of the hotel. Now the first floor only has one wing. The first floor only has an S wing. There's only one sublevel to that floor. But the second energy level has two sublevels. It has an S wing and a P wing. So these S and these P, these are going to be our orbitals. There's S orbitals, there's P orbitals. In my S orbitals, I only have one type of S, and it holds two little electrons. Okay, two electrons per orbital. In my P orbital, each one of these, there's three different P orbitals, or three different kind of rooms, if you want to say, three different P orbitals, or three different rooms in that region of the hotel, the electron hotel. So I have the px, the py, the pz based upon their orientation. Okay, so each P, we have three different orbitals there. The S only has one orbital. On the third floor, we have three sublevels. We have an S, a P, and we have a D. Okay, the D actually has 5 orbitals based upon their different orientations. So the D region of the hotel, you could think of it has 10 rooms, and each one of those rooms is an orbital, and each one of those orbitals can hold 2 electrons. Okay, so we have our 10 electrons, and as you kind of go through this table, you'll see the patterns. And lastly, we have an F orbital. The F orbital has 7 different orientations for this orbital, and each one of those orbitals hold 2 electrons, giving me 14 total. So this hotel, as we go up in energy level, we keep adding different sublevels, and as we add sublevels, each one of those sublevels has a certain number of orbitals. Okay, and you can use this table as kind of a handy way to navigate this. So what electron configuration is it's taking the order that the electrons will fill this hotel, and it's always going to be the order of lowest energy to highest energy. Okay, electrons always fill from lowest energy to highest energy. Okay, low energy is good. Electrons will go there first, and then they'll go to the higher energy, kind of more crazy upper levels to this electron hotel. So what we're going to do is we're going to use some rules to determine the electron configuration. So which rooms fill up first? Which orbitals or energy levels fill up first? So the first principle we need to look at is something called the Aufbau Principle. The Aufbau Principle says that electrons are going to fill up those lowest potential energy orbitals before the higher potential energy orbitals. So there's a order for this. And Aufbau was able to come up with the order for increasing potential energy for the orbitals described by Schrodinger's wave model. So the 1s is going to be the lowest potential energy, and the 7s is going to be the highest potential energy. So as I'm going 1s, 2s, 2p, 3s, 3p. Now remember, in the third energy level, there are 3 sublevels. So there's my third one over here, the 3D, but for some reason the fourth energy level actually fills up first. It kind of breaks our perfect trend. And the reason this is that the s orbitals are kind of that spherical shape. There's what's kind of called this nucleus penetration factor. Those little electrons like to be near that positively charged nucleus. So the s orbital is actually lower energy or easier to fill than the d orbital, and the d orbital is kind of that weird, funky, all kinds of weird, funky shapes, because in a d orbital there's 5 different orientations there, and it can hold 10 electrons, and all those electrons are going to repel against each other, and it's kind of a really high energy situation. So the 4s actually fills before. So as you go through this order, it kind of has some weird exceptions. The 6 over here is before the 4, but that's based upon this idea that the electrons are going to go to the lowest energy first, and there's some weird exceptions there. But to do these problems, you're going to have to take this relationship, and we're going to look at this in a second. And this is the order that we fill the rooms in. So we're going to do that in a second. Another rule we need to keep in mind is Pauli's exclusion principle. It says that no more than 2 electrons can stay in the same orbital. So if I have let's say I have a 1s orbital, we can't have more than 2 orbitals in there. So I can only have 2 electrons per 1 orbital. So here's my little 1s orbital. Let's say I have a 2s orbital. It's the next one that gets filled. So I can only have 2 electrons. Hund's rule says if I have, okay, let's do that first. So we can have 2 electrons. They're going to spin in opposite directions. Okay, electrons repel each other, so they spin in opposite directions. So I'm just going to draw a little line to kind of indicate the difference there. Sometimes you may see an up arrow and a down arrow, which represents they spin in opposite directions. You may see your 2 electrons in that 1s orbital indicated like this. So they can hold 2, and they go in opposite directions. They're spinning in opposite directions. Hund's rule says if I have something like p orbitals, okay, so let's look at the 4p. In the 4p there are 3 different orientations, the x, the y, and the z. So each one of these only can have 2 electrons based on Pauli's exclusion principle. But Hund's rule says because electrons are repelling each other, they want to be away from each other, they actually fill up 1 electron per each orbital before they start filling up 2 per each orbital. So what's going to happen is my little px, my py, my pz, you don't have to know what the orientations are, but electrons are going to kind of spread out. So I have my little p orbital here. Okay, I have my y, my x. Okay, I have my pz orbital. My electrons are going to start filling in 1 electron per orientation before they start filling up. So if I had 3 electrons in the 4p orbitals, they would fill like this. If I had 4, I'd start crossing over. Okay, so they each spin opposite direction, but I fill 1 in each first. Okay, that's Hund's rule. So I'm going to apply all these 3 principles into actually doing an example problem. So let's look at tin on the periodic table. I look at the periodic table, and tin is the atomic number of 50. We're going to assume that it is neutral. Tin's atomic mass is, I'm looking at the periodic table, about 118. This is average the atomic mass, 0.7 is my atomic mass. The element name, Sn, or tin, excuse me. This is tin. Okay, so what we're going to do is we're going to do and find the electron configuration. So my electrons are going to fill in this order, okay, based on the Aufbau principle, from lowest energy to highest. So I'm going to take 50 electrons, because we're going to assume that this is neutral, 50 protons, 50 electrons, and I'm going to make 50 dashed lines representing electrons. Okay, and if they spin in the opposite direction, they're going to go the other way. So I'm going to go ahead and start, and I want you to watch carefully what I'm doing. Okay, so I have the first 2 electrons, 1, 2. We're going to fill the 1s. Okay, first 2 electrons, so I put 2 in here. Then I'm going to fill the 2s, 3, 4. Okay, now I'm up to 4. Now I'm going to go fill the 2p, 5, 6, 7, 8, 9, 10. Now I'm at 10 electrons. Okay, now I'm up to 10. So now I'm going to go 3s. I need to get to 50. So now I'm going to go 3s. 11, 12, 13, 14, 15, 16, 17, 18. Now I'm up to 18. Okay. Still have a lot more to go. Let's go 4s. 19, 20. Go to the up to 20. Now I need to jump to the 3D is the next lowest energy. So I actually have to go over to 3D. We're at 20. I'm going to go 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Now I'm up to 30. Then I need to go to 4P. I need to get to 50, remember. So 4P, 31, 32, 33, 34, 35, 36. Okay, now I'm at 36. Now I'm going to go to 5S. 37, 38. Now notice I'm not going to 4D yet because 4D is actually higher energy. So we have to fill the S first. So I'm going to fill the S. Now I'm at 38. Now I need to go 4D. Now 4D holds 10. 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48. Now I'm at 48. And I need 2 more. So I'm going to go look at 5P. I only have 2 electrons left to fill, and I'm going to go 1, 2. Pauli's exclusion principle says I'm going to fill 1 electron in each of the 5p orbitals before I fill 2 and 1. Okay, so I'm not going to do this. I'm not going to do 5p. I'm not going to go 2 and 1. Okay, I have to fill 1 in each orbital first. So we're going to use this order. We're going to make sure that we're filling in 1 into each before we start filling 2 into 1. And we're going to make sure they spin in opposite directions. So you're going to do this for 12, and you need to make sure you do these slips so that by tomorrow when we do our lab, that you and your group members are going to be able to do the activity. I hope this was helpful. You have a pleasant evening.